All right. Does anyone have any questions on the homework from Friday? What number? It was pages 23, 24. So does anyone have any? So I'm asking is, does anyone want me to go over anything? Do you really need me to go over it? I was just asking because there was some doubt in your voice. I can do 3. All right. So I'm going to quickly go over parts of the homework if you have questions on it. So I'll do 3, and we'll go from there. I'm not going to go over the whole homework. If you need to see like answers and stuff or check your work, the keys are posted in Canvas. Okay. So 3, the 8-sector spinner is back. The spinner is spun once and the outcome is noted. And we're going to answer the following questions. So we're going to let event S be the event of getting a perfect square, 1 or 4. Those are really the only 2 perfect squares on there. What is the probability of getting a perfect square? So how many options on this is a perfect square? There's 2. Okay, how many options total? Yep. So 2 out of 8, that simplifies down to what? 1 over 4, which is what is a decimal? 0.25. Yep. All right, so that's the probability of getting a perfect square. So my perfect squares again are 1 and 4. Now let E be the event of getting an even. What's the probability of a perfect square given you got an even? So before we even attempt that problem, remind me again what the conditional probability formula is. This is a conditional. So I have the probability of A given B. So I have the probability of A given B. What's that the same as? Back to your notes, the formula. We've done this like 1,000 times last week. The probability of blank over blank. So what goes in the numerator?
Probability of A.
Not just the probability of A. Probability of A and B. So the probability of both.
Over the probability of B.
Right. Over the probability of B. And remember, B is your given. So an easy way to remember that formula is the probability of both over the probability of the given. Okay? But that's kind of how you would write out in legal terms. So we're doing a conditional probability for this problem. We're finding the probability of getting a perfect square given we got an even number. So probability of S given E. And they want to know, are the 2 events independent? So first off, let's just find the conditional. So probability of S given E. What's the probability of both happening? So in other words, we get both. So if we rewrite this, it's the probability of S and E over the probability of E. So what's the probability of getting both a perfect square and an even number on that spinner? So how many outcomes are both a perfect square and even? 1. It's the 4. So 4 is the perfect square and it's also even. So what's the probability of getting that 4?
1 out of 8.
1 out of 8. So that's what we're going to put on top. Over someone besides Owen was the probability of getting an even number on that spinner. How many outcomes are even on that spinner? 4. So 4 out of 8. So in your calculator, remember how I told you to type it in last week? Type this in. Remember to put the parentheses around the two fractions. And tell me what you get. I want as both a fraction and a decimal. So it's 0.25. What's that as a fraction? 1/4. So we get 1/4 or 0.25. So here's the question. Are these two events independent? Can someone define for me what independence means? So we talked about this on Friday. What does it mean for two events to be independent of each other? Look back to notes if you need to. What does it mean for two events to be independent of each other? It doesn't change the probability of an event happening. So in other words, independence can be found by this formula. It just means that if you take the conditional probability of A gets B, it should equal the probability of A if they are independent. Okay? Meaning B does not change the probability of A. If you know for a fact that it falls into set B, still does not change the probability of A. So are these two events independent of each other? And how do you know? So set E and set X independent of each other. Give me a hint. Look at the previous question too. So are they independent of each other? Yes or no? Oh, they're absolutely independent of each other. Why? Because they're both the same probabilities. If I replace A and B with S and E, we're saying the probability of S given E is equal to the probability of S. Did we find both of these already? Yeah. Aren't they the same probability? Yeah. So in other words, they are independent of each other. Okay? So guys, whenever you see these formulas, just replace the values that were given with the values that are there. So like S would be A, S would be A given B. Okay? And then you can line up and be like, okay, so those two match up, those two match up, those two match up. That makes sense. Looks like we got it. Okay? That's why I always have you guys rewrite these formulas out using the letters so that at least you know what you're talking about. All right? So, yes, they are independent. So they're independent because E does not change the probability of S. Okay. Last one. Let M be the event of getting a multiple of 4, meaning if you divide that number by 4, meaning that it's a number divisible by 4. So multiple of 4 means it's a number divisible by 4. What is the probability of getting a perfect square given that you got a multiple of 4? So we call it P of S given M. So that means that if we were to rewrite it using the conditional probability formula, what is that? So what would the numerator be if we find the probability of what? Blank and blank. Replace A and B with S and M. Guys, I know you can plug things into a formula. Come on. Right, the probability of S and M over the probability of what? M. So remember, conditional is the probability of both over the probability of the given. So, how many outcomes on here are both a perfect square and a multiple of 4? Meaning that it's divisible by 4. 1. It's just the 4. 4 is divisible by 4. It's also a multiple of 4. Uh-oh. 1 second, guys. Chromecast is being dumb. So that'll be 1 out of 8. Over. How many outcomes on here are a multiple of 4? Meaning that they are divisible by 4. 2. So the probability of that happening is what? 2 out of 8. So put that in your calculator. Tell me what you get as both a fraction and a decimal. One half.
0.5.
1/2 or 0.5. So my question is, are these two events independent? So is getting a perfect square and getting a multiple of 4 independent of each other? No. Why? Because they're different. So if you look here, we have, so they're not independent because P of S given M, so the probability of perfect square given multiple of 4 is not equal to the probability of getting a perfect square. This one is 1/4, this one is 1/2, two very different numbers. So does that kind of clear up any issues with figuring out independence? Any other questions on the homework? Okay. So let's go ahead and get into the notes for today. So go back to page 25. So we've talked about how to find independence, we've talked about conditional probability, and we talked about the addition property of probability. So just to review, so this is conditional. That's independence. Who remembers the addition property? So this was like 7.3. You want to look back. First off, we use the addition property when we're trying to find the probability of what? A starts with a U. We're trying to find the probability of a, look back at your notes, 7.3, a union. So in other words, we're trying to find the probability of A union B, or what's the other name for union? What's the small word that represents union? Nope, or. Intersection in scan. So we're trying to find A or B. Okay. What's the formula for that? So remember, think about a Venn diagram. The union would be the entire Venn diagram, at least within the circles. So what's the formula to find a union? So we know we're going to be adding the two main sets probabilities. But what's the issue? We talked about this a lot last week. What's the issue if I just add these? Was it not account for? Think about your Venn diagram. It accounts for what? So here's set A, here's set B. When I drew those circles, what kind of got circled more than once? Set A, set B. The intersection. So the intersection gets found twice, or the and. So how do I take care of it? I subtract it out. Remember that symbol means and. And the or symbol, I'm actually just going to that means or. Remember, or means at least one and means both. So this was the other formula we talked about. These are the three formulas that we talked about so far. Besides the obvious, basic probability formula, which that one should not be hard for you guys. So we've done addition, we've done conditional, we've done independence. Now we got to do multiplication. So think about this logically. If the addition deals with the or, what do you think the multiplication is going to deal with? The and. So addition is the union and is going to be the intersection. So probabilities involving single-step experiments are easy enough because only one thing is happening to affect the probability. So in other words, for example, you flip a coin once, pick one person at random, you pull one card out of a deck. Probability is both empirical and theoretical, so empirical is another name for experimental, become increasingly more complicated with multi-stage experiments. So we've kind of seen that already when we were doing Venn diagrams. So you flip a coin 3 times. That's an example. How we handle these types of probabilities actually comes from the conditional probability formula. So given the probability of event B occurring given event A has occurred, we're given this formula. So that's the conditional probability formula that we're fairly used to. So we're going to rewrite this formula solving for P of A and B. So we got P of B given A is equal to P of A and B over P of A. I want to get this part by itself. How do I get that by itself? In other words, how do I get rid of the denominator? So think about if P of A was like a 2. How would you get rid of that number? So guys, if I had 1 equals x over 2, how would I get rid of this number to solve for x?
You would multiply both sides by 2.
Right, we will multiply both sides by 2. So how do I get rid of P of A?
You would multiply both sides by
P of A, yep. That goes away. I get P of A times P of B given A is equal to P of A and B. Now, how could I write this formula if the events of A and B are independent? So let's look again at our formula for independence, okay, which is right here. If we know that A and B are independent of each other, That means I got P of B given A is going to be equal to the probability of B happening. So if I know for a fact that they are independent, that orange statement is true, what could I replace this one with? What can I replace that with? If I know for a fact that orange statement is true. So we know that this is true. What could I replace this with then? Kind of already on the board. Not A and B. Do we have something that we just said that this is equal to? What is it equal to? P of B. So guess what we can replace it with? P of B. I can replace P of B given A with P of B because we know they're independent. So this would be P of A times P of B is equal to P of A and B. So these two formulas, this is the multiplication rule. This one is when they are independent of each other. And this one is when they're not independent. Just so you know. But the one that we mainly want to focus on, or at least that you'll probably see the most of, is this one. So, this arrangement of conditional probability formula gives us a useful tool for calculating the probability of events that occur in multi-stage experiments. You will easily be able to accomplish this if you systematically phrase the questions of intersections and events. Remember, that is an and statement. So, for this next exercise, consider the spinner below. The spinner is spun twice, and the results are recorded. So, are the outcomes of the two spins dependent or independent of each other? So, in other words, if I spin that spinner twice, does the outcome that I get on the first spin affect the outcome that I get on the second spin? Nope. It's not like I'm taking a number away. It's not like I'm taking a section out. So, they are independent. So that means since they're independent, that means I can use this rule right here for any questions. So, what is the probability that you will get an that you'll get an even on the first spin and a number greater than 5 on the second spin? Okay, so we have right here an and statement. Meaning, we're trying to find the probability of getting in on the first spin an even and on the second spin a number greater than 5. Actually, I'm going to use F and S. First spin even, second spin number greater than 5. So if we use the formula that we just came up with, so that would be this formula right here. So that would be P of A and B is equal to P of A times P of B. So that's the formula we just came up with. That's the multiplication. How would I use it? So how would I rewrite this and statement to look like that formula? because we already know they're independent, so I can use that formula. P of FE times P of S is greater than 5. So I got to find the probability of the first happening, probability of the second happening, multiply them together. So what is the probability that I will spin an even number? So how many even numbers do I have on the spinner?
You have 4.
I have 4. 2, 4, 6, and 8. So what's the probability that I will spin an even number? 4 out of 8. Times. What's the probability that I'll spin a number greater than 5? How many numbers on here are greater than 5?
3.
3. 6, 7, and 8. So I have 3 out of 8. So when we multiply fractions, how do I multiply fractions? So remember, this is the probability of the first spin being even and the second spin being greater than 5. How do I multiply fractions again? I multiply straight across. So don't cross multiply, you multiply straight across. So this will be 12 over 64. What is that simplified? You're doing your calculator, just type it in, hit math, enter. It's what? 3 over 16. Good. What is that as a decimal? You can round to 2 decimal places if need be. It's what? 0.19. So it's approximately 0.19. So in other words, the probability that I will spin an even number on the first and a number greater than 5 on the second spin is about 19%. So about 19% chance of that happening. So what is the probability that you will spin a prime number and a perfect square in either order? So note that this is more complex than B. So let's think about this one for a second. So you'll spin a prime number and a perfect square, but in either order. So in other words, we got to check the probabilities of them happening if we switch the orders. If they're the same, that'll be about what it is. Okay, otherwise we got to do a bit more with it. So we're first going to check the probability of, let's say, a prime number on the first and a perfect square on the second. Okay. So what's that probability? So what's the probability? So this will be a probability of the prime times the probability of a perfect square. So what's the probability of getting a prime number? So how many numbers on this spinner are prime? Meaning they can only be divided by 1 themselves. So how many? Not quite. What are the numbers that are prime on here? 1's not prime, 3's prime, 5's prime, 7, and there's one more. I'll give you a hint. It's a number that you don't think it would be. 2. 2 is technically prime. It's the only even number that's prime. So there's 4 outcomes. So we got a 4 out of 8 chance of it being prime. How many numbers on here are perfect squares? 2. So 2 out of 8. So I got 8 out of 64. So that'll be 1/8. Now, let's say that I did it in the opposite order. So I did S given P. So I got the probability of S times the probability of P. Yeah. Take a minute, calculate that one on your own, using the same formula essentially. You guys got it? Shouldn't take you very long. Okay, walk me through it. What's the probability of getting a perfect square? We kind of already found it. 2/8. Probability of getting a prime. 4/8. So that's 8/64, still 1/8. Now, we're not done. Our answer is not 1/8. Because it then says that in either order. So in other words, we don't know which order happens. We just want at least one of them to happen. Hint, hint, wink, wink. So here's my question. We want at least one of them to happen. That means I need to take these two probabilities and set it up as a what type of statement? We want at least one to happen. What do we know that stands for at least one? So what? Addition. So in other words, we're setting it up as a union or an or. So this means that we're going to do an or statement because we want at least one of those two to happen. Either the prime coming first or the perfect square coming first. We don't care. So we want the probability of P and S or the probability of S and P. Now here's my question. We know that with this one, we use this one if there's overlap. But let's think about this logically. Think about the numbers that were prime for a second. 2, 5, 3, and 7. And the ones that are perfect squares, 1, 4. Is there any overlap? Are there any numbers that overlap that I just said? So the prime numbers that were on that spinner. So the prime numbers that were on that spinner were 2, 3, 5, and 7. The perfect squares were 1 and 4. Is there overlap? No, there's no overlap. So if there's no overlap, do we have to worry about subtracting out hands? No. These two events are what to each other? I'll give you a hint. ME. What does that stand for? Mutually exclusive. Good. Meaning, if I was to draw it as a Venn diagram, they'd be two completely separated circles and not overlapping. So we can simply just add these two probabilities because there's no overlap. Yes. Yeah. So there's no overlap. So that means we can just add the two. So we can do P of P and S plus P of S and P. So that'll be 1/8 plus 1/8. What's 1/8 plus 1/8?
2/8.
2/8. Which that simplifies down to what?
1/4.
Or 0.25. So we have about a 25% chance of spinning a prime number and a perfect square in either order. So guys, that's another thing you gotta be careful about when you do those or statements. You gotta ask yourself, is there overlap? If there's not, you can just flat out add them. But if there is, you gotta subtract out that overlap. Okay? So be careful. So there was no overlap, so I just flat out add. All right? Now, here's where it gets a little bit more complex. Okay? So as experiments grow even more complicated with more stages, theoretical probability become increasingly more complicated. It is especially important to note whether you are sampling with or without replacements. So everything that we've done so far has been with replacements. Or at the very least, there was no way you could replace anything. Like there wasn't anything to replace. So everything we've done so far has been either with replacement or there wasn't anything to replace. So remember, that doesn't always happen. So a class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. If the students are picked at random, what is the probability that they will all be boys? So the probability that they will all be boys. So let's think about this logically. Let's say that I used my cup with my numbers on it and I pulled 3 names out of it. And I wanted the probability that they would all be boys from this classroom. First off, if I pick 3 people, do you think I want to be putting those sticks back in the cup? No. So this is going to be a without replacement scenario. So this is definitely a without replacement scenario. So that's just something to think about. First off, how many students do I have total? 20. So I have 20 students total. So event 1 is that the first pick was a boy. Event 2, second pick was a boy. Event 3, third pick was a boy. So if we want all 3 to be boys, that means we're going to set this up as a what type of statement? Or and. And we want all 3 to happen. So we want the probability that E1 and D2 and D3 will happen. So we can do this in terms of multiplication. So we're going to want the probability of E1 times the probability of E2 times the probability of E3. Now, remember, it's without replacements. So you got to think about this logically. So the first one is always the easiest. So out of my 20 students, what's the probability that I will pick a boy on the first go?
8 out of 20.
8 out of 20. Now, I picked that boy. So I had 8 boys originally, but I picked that boy. So how many boys do I have now? I have 7 boys now. So going into E2, I have 7 boys. How many students total? 19. 19 students. So what's the probability that I'll pick a boy on the second round? 7 out of 19. Okay, so that means I picked 2 boys out of my original total, 2 students out of my original total. So how many boys do I have now going into E3? I have 6 boys, 18 students. Do you guys see how this is working? Okay. I'm assuming that what I picked was a boy. All right, so I can subtract from the boys, don't subtract from the girls. So the next one is 6 out of 18. So I want you guys to type this in your calculator and tell me what you get is both a fraction and a decimal. Don't forget to put parentheses around those 3 fractions. It's what? Ew, it's ugly. Yeah, let's see if it even converts to a fraction. Okay, so as a fraction, it's a doozy. The fraction would be 14 out of 285. So it's a pretty darn small chance that it's going to happen. So if I round that to the nearest hundredth, the decimal, it would be 0.05. So as a percent, what's that as a percent? About how much? 5%. So it's a pretty low chance that that all 3 of your picks are going to be boys. Pretty low. Doesn't mean it can't happen, but it's not very likely that's going to happen. So do you guys understand how the without replacement is? Okay, so you got to remember when you go into the seconds, you took one of the boys out, so that means you took one of the students out. Going into the third, you took 2 of the boys out. So you got to remember to subtract as you go if you don't replace. And you assume that what you did happened, or what probability that you put first happened. So we assume that a boy was taken out for the first and the second, and so on and so forth. All right. Now, the multiplication property of probability is crucial in many applications in engineering decision making. So a lot of times, when it comes to engineers, so if you ever thought you want to be an engineer one day, you'll probably be using this a lot. So a lot of times engineers, when they're like, yeah, this bridge is safe, they got to have a pretty darn good probability, okay, that bridge ain't going to just, crumble in 2 seconds as soon as a car goes on it, okay? Or if they're like, yeah, that drug is safe, or this machine is safe, it's not going to kill anyone. And again, they got to have pretty high probabilities. That's pretty morbid, but the truth's the truth, okay? In other words, they got to cover their butts so they don't get sued. That's a good life lesson. Most of the time, you're covering your butt so you don't get sued. It's typically how that is. So say that a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches would fail is 5%. What is the probability that all 3 will fail given the switches are independent of one another? Meaning that if one of them fails, it's not going to cause the other 2 to fail. Okay? So we know for a fact that they're independent. So we don't have to worry about like the without replacement thing. Without replacement automatically means it's not independent. So how do you think I would go about this? Wait till someone gets back. So how would I go about this? So we want all 3 to fail. So that means I need the probability of a what type of statement? Or and. And. So I want to know what's the probability of 1 failing, 2 failing, and 3 failing. So in other words, we're screwed. All right. All 3 of the safety measures have failed. And again, these switches are independent, meaning if 1 goes, it's not going to make 2 or 3 go. Okay. How do I find it? Think about this. Think about your formulas. Which one am I using for ands? Sure. Can I get a pass? You multiply them. So we got to find the probability of 1 times the probability of 2 times the probability of 3. What did they say is the probability of any of those switches failing? About 5%. Now, my recommendation, convert that percent to a decimal. So what's 5% as a decimal? 0.05. So we're saying that the probability of 1 failing is about 0.05 or 5%. Probability of 2 failing is 0.05. Probability of 3 failing is 0.05. So what's the probability of all 3 failing? So multiply all 3 together. I think. Yeah, it is. It's 0.15, which is what is a percent? So we got a 15% chance of all 3 of those switches failing. I mean, it's not a bad probability, but it's still a little bit more high for my liking. Most engineers, they typically want that to be in the lower than 10 range. Okay. So 15% chance, still a little too high. It's low, all things considered, but in terms of like human safety, that's a little bit too high. Okay. So are you guys understanding how to use that multiplication rule? Basically, with ands, you just got to ask yourself, is it independent or not? Is there a replacement or not? More often than not, they'll flat out tell you. Or it's going to be like really like straightforward, like, oh yeah, this is going to be independent, or this is going to be dependent. There's going to be a replacement or whatever. Okay, last one. So many times when using the multiplication rule, we need to be careful about how we frame the question. But if we properly frame it in terms of and or as logical connectors, then the rules of probability will work out. So remember when I said that like I hate probability? This is why. A lot of times you got to read it really, really, really carefully, because 1 or 2 words can make all the difference in probability. So a company is determining the effectiveness of its warranty sales on computers. They took data on the number of customers who purchased warranties on 2 different brands. If a customer was chosen at random, what is the probability they did not purchase a warranty? So the probability that they did not purchase a warranty. So let's look at those tables. So this is the percent of customers who are purchasing a computer. So they purchased a computer. This one is the percent who purchased that also purchased the warranty. So these people added on the warranty. Okay. So let's think about this logically. So this is kind of a two-way frequency table in a way. Not exactly, but it's close. Specifically, at least the columns. If you add up the percentages of the columns, or at least the first column, what does it add up to? 100%. So this first column is going to add up to 100%, which makes sense because of this company's customers, they only have two different computers, so the customers are either going to be buying A or B. All right, one or two. But these 35 and 50%, 6%, where are they coming from? So those are the ones who purchased computers that also purchased warranties. So in other words, are we talking about 35% of all customers or 35% of the customers that bought Type 1 computer?
35% of the customers that bought the Type 1 computer.
So in other words, 35% of that 68% of customers. Same thing with Type 2. 56% of that 32% bought the warranty. Okay, so that's a lot of numbers. So let's put it this way. Let's just make a scenario that they were looking at 100 people. So 100 people bought computers. How many people bought Type 1? 68. So we're saying 68 people, and I'm just making these numbers up, but it kind of helps put it more into reality or put it more into a clear picture. So 68 people bought Type 1. How many bought Type 2? 32. So of that 68 people, how many bought the warranty? 35%. So find what 35% of 68 is. So multiply by what? So you take the 68 multiplied by 0.35. So how many people? So if you multiply 68 by 0.35, it's about 20. It's 23.8. So about 24 people. So I'm going to say 23.8, but just know that also means 24. So of the 32% of people, how many bought the warranty for Type 2? So you're going to do the same thing. Multiply it by 0.56.
About 18.
It's about 18. So it's 17.92, which is about 18. Okay, so that's just to put it into perspective. Now we want to know how many did not buy the warranty. So let's think of it this way. Okay, we got the number of people that purchased. We want the ones that did not buy the warranty. Okay, so if we think about it, we want the probability that they bought the Type 1 computer and no warranty. So in other words, it's the warranty complement. So that just means no warranty. We also want the probability that they bought the Type 2 and no warranty. So let's think about it this way. If 35% bought the warranty for Type 1, how many did not? Out of 100% of Type 1.
65%.
Right. So that means that 65% of that 68%, no warranty. If 56% bought the warranty for type 2, what percentage of the 32% did not?
44%.
44%. Again, no warranty. So, we can do multiplication rule for this. So, the probability of them purchasing a type 1 computer times the probability of them not getting the warranty. So, what was the probability of them buying a type 1 computer? What does it say? So, the probability of customers getting a type 1 computer, 68%, which let's put it as a decimal. 0.68 times what's the probability that they did not get that warranty? That they did not get the warranty. 0.65. All right. Equals. All right. So put that in your calculator. Tell me what you get. Yep. So we're saying that about 44% of that 68% of people did not get that warranty. Okay. So the other one, we're going to do the same thing pretty much. So T2 times no warranty. So that would be 0.32, which is the probability that they buy a type 2 computer, times 0.44, which is the probability that they don't get a warranty for that computer. So what would that be? So that's 0.1408. Now, they want the total that they did not get a warranty. So that means that they either got the type 1 and no warranty or the type 2 and no warranty. So what do you think I got to do to add these two to do with these two warranties? So listen to how I said it. They want to know whether they got type 1 and no warranty or type 2 and no warranty. So they want to know whether they got this one or this one. So how do I calculate? Nope. Addition. Keyword. Or. So we want the probability that they got T1 and no warranty or T2 and no warranty. All right. And we're assuming there's no overlap, okay? Because if you look, these completely add up to 100%. Okay, so since they add up to 100%, we can assume there's no overlap. So we just add these two probabilities. So 0.442 plus 0.1408. So what's that probability? So if you add those two together, what is it? .5828. So we're saying if we convert that to a percentage, that about 58.28% of people that bought a computer did not buy the warranty, which honestly, that makes sense. Most people don't buy those warranties. So guys, you got to think about those like really, really carefully. So sometimes you got to do an and statement mixed with an or statement. So you're doing two ands and then you mix them together. Any questions? All right, so your homework for tonight is pages 27 and 28. So you got about a solid little over 20 minutes to work through that. As you guys are working, I'm gonna come around and check off your homework from Friday. So that was pages 23, 24. Yes, ma'am. Yeah. So go ahead and get to work. I will come around and check off those homeworks.